Awesome. Thank you, Tanya. Could you send the link to the spreadsheet again? Just
Yes.
real quick. Yes, so just out of curiosity, who here today was also here yesterday? Could you give me a green check mark if you were and you attended Intro to Linux? Seems like most people. So most of you probably already have a training cluster name claimed. So if you could log in again, it's the exact same setup as what we had yesterday. You need a terminal and also log in to the training cluster. So I'll log out and I'll log in again just to demo. So I am user 098. I'll scroll down to where I claimed mine. I'll copy and paste. I can SSH user 098 at basics. You would do whichever username you are, enter. And now I have to enter the password, which I will copy and paste again. Because for me, that's just a single right click. And note that on Linux, it doesn't tell you, there's no cursor or indication that you're typing. I should be all logged in. I'm just going to clear this feedback. Can you give me a green check mark once you've logged into your training cluster account? And if you're having any issues, please let us know. I'm going to be working on the training cluster the whole time. Yep, you don't have to. Can you use terminal? As long as you're able to SSH. We recommend MobaXterm, but there's other terminal programs. I guess I'll send the link again to the spreadsheet. So when you're on the spreadsheet, you find an empty row and you can claim it by writing your name there. And then this is this column C, that's the command that you enter for connecting to the training cluster. And then everybody has the same password because it is a training cluster. We're not going to be storing any important information here. So once everybody has that, if you could give me a green check mark, if you're having any trouble, please message a helper or let us know in the chat or with a red X. Carry on slowly. So as Tanya already mentioned, AceNet's a not-for-profit. I won't go too deep into this just because if you're following the training, we have a whole session all about what is AceNet and how we fit into the national infrastructure team. But essentially, we're a not-for-profit. We provide researchers in academia, industry, government with access, expertise, support, and training for digital research tools. So we provide access to both compute power and storage. We have a local team. Our AceNet team is located all around Atlantic Canada at different universities and institutions to help the researchers and industry members there. We do a lot of training, which is what we're doing right now. We're also a regional partner of the Digital Research Alliance of Canada, which I'll talk about on the next slide a little bit. And so another thing about AceNet is your data remains in Canada and we have no intellectual property interests. We don't care about your data. We just want to help you further your research and further research in the region. And all of AceNet's services are also free of charge for academic researchers and academic or industry collaborations. And so we're part of a national federation. So we're the regional partner of the Digital Research Alliance of Canada, also known as DRAC, which is the national umbrella organization for research infrastructure. So their purpose is to oversee the delivery of advanced research computing, research data management, and research software nationally for the Canadian research community. They also ensure that these things are open and equitable, or the access to these things is open and equitable for all researchers, and to generally improve and increase the availability of digital tools and services. So ACENET partners with DRAC and also other regional organizations in different areas of Canada that are similar to ACENET, such as Calcul Quebec in Quebec and SharkNet, SciNet, Compute Ontario, etc. And so this is so we can all do the best work we can improving access to resources across the country. So it seems like people are still getting logged in, but I still have to talk a little bit more, so you have time. So I'll talk a little bit about what we're going to do today, which is shell scripting. So we'll talk about it in terms of an imaginary grad student project. So imagine we have a sample workflow that a student or a researcher might be following. We have some sort of analysis program that we've written, that's the start, and we have to run it on a whole bunch of different test inputs, probably hundreds of times, tabulate all of those results, and then see if we're ready to publish a paper or add it to our thesis. If so, great. But if not, we would have to go back, modify our program again, running all the tests again, and so on and so forth. So the nice thing about using the command line is that it's very handy for automating tasks on your computer using only a few commands. So today what we'll do is we'll build on what we learned yesterday, learn a few more commands and techniques, and put them together using our sample workflow as a framework for this. So next, what we have to do is download the program and input data that we'll be using today. So I will do this for mine. I'll copy the link that we'll have to enter. So the command, I'll copy that into the chat. So paste it into my terminal. So it's wget and then a link that'll download the files that we're going to be using today. Hit enter. You'll see a bunch of output. And then I'll type ls once that's done, just to see now I have something scripting.zip, which is what I want. Once you've downloaded that scripting.zip, if you could give me a green check mark. So it seems like everybody in the chat has managed to log in. At any point, questions are more than welcome in the chat, or you can private message a helper if it's something specific. Awesome, awesome. Okay, so once you have the scripting.zip, next thing we need to unzip that so we can actually use it. So the command for that is unzip space and then the name of what we're unzipping, scripting.zip. Enter. And now if I ls again, I'll see scripting.zip is still there, but now I also have a directory called scripting. And so once we have that downloaded and unzipped, we will change directories so that scripting is our working directory and we'll be hanging out in there for the rest of the session. So now I'll type cd, change directory, space scripting. I'll use tab autocomplete. I'll also type ls, have a look at what's in there. And so once you've changed directories, once scripting is your working directory and everything's downloaded and unzipped, if you could give me a green check. Once you have this done, that's all the download and setup for today. So we have a few files already prepared for you. We'll be seeing what's in them or using them all at some point. Okay, yes, for anybody who came in late, helpers are ready. You have to, it's the same setup as yesterday. If you were here yesterday and you already have a login claimed from the spreadsheet, you can use the same one. I'll copy the line in for downloading the data again into the chat. So the main thing that we're going to be working with today is this run-numal. Or sorry, not run numal. We have numal, which is an imaginary program that we've written for demonstrative purposes. So this is our program's name. The first thing we're going to try and do is we'll try to run this program. And I'll just type the name numal and hit enter. So first thing, we can see that doesn't actually work. So when we're running a program, we're going to have to be a little more specific about where to find the program. So what we'll do is we'll use the shortcut for our current directory, which is a single period, and write a mini path to our executable. So I'll do period slash numal. And this program I know needs an input file. So we'll use the less than symbol. I'll put a space, less than symbol, followed by our input file name to tell this numal program where to find input. So I saw earlier, I have a few different files here that end in .in. These are all different input files that we'll be using today. So I'll type methane.in, and that will be our input file. It kind of looks like you're making an arrow from the input file into the program. So now I'll execute the command and we'll see what happens. So I'm getting some output. It says this is numal, kidding. And then after a couple seconds, it says the energy is -5. So this numal program is supposed to calculate the energy of whatever molecule structure that we input. So in this case, it was methane. The real program does actual chemistry, but this program, I believe it just counts the number of lines in the file and then sleeps for a few seconds to pretend that it's doing something, to pretend that it's doing all these calculations. So we have our input, or sorry, we have our output. It printed to the terminal screen, but it didn't get saved anywhere, so it's not all that useful to us yet. We have to redirect the output so it's printed to a file, not just our screen. So if the less than symbol is used to direct input, can anybody tell me what symbol they think is for directing output? You can let me know in the chat. Yeah, yes, the greater than symbol. So let's run our program again, this time redirecting the output to a file called methane.out. So what I'll do, I'll hit the up arrow key once to go into my command history. And so this will give me the most recent command that I entered. I can press the up arrow again and keep going further back into my history, or I can press down to go back down. It's a very handy shortcut for when you're working with the command line. So I'll bring back my most recent command, /numal with less than methane.in. I'll do greater than symbol and we'll type methane.out. So the output file that we specified doesn't already exist, but it'll be created when we run the program. Well, before there were no .out files in our current working directory, but now that this is done running, if I type ls, I should see now I have a methane.out. And we can use the cat command, short for concatenate, to have a look at what that output looks like. So I'll type cat and then methane.out. And we can see this is what the content is. It's the same output as when the output just got printed to the terminal. So we have a few files that have this .in extension, and these are more input files that we have to run NuMal on. Let me just flick back to the slides really quick. Yes, so in reality, we can imagine that we have hundreds of these input files that we'd need to repeat essentially the same line of code over and over and over, changing our input and output file names every single time. Can anybody suggest some reasons why this would be a bad idea? You can also let me know in the chat. If this is our workflow so far, we have to type /NuMal, methane.in, methane.out, /NuMal, ethane.in, ethane.out, and so on and so forth. What is wrong with that workflow? See, the file names are different because we have .in and then .out. Yeah, people are saying it's long and it's slow. Every single time you have to type it in. Yeah, basically it would take a really long time. It'd be very error prone, so you very well could make mistakes and overwrite files and make all kinds of mess because you're manually typing things. And it's just boring. Nobody wants to sit there and just type the same line over and over, making tiny changes. And then another thing, a bonus sort of thing is it doesn't really follow computing cluster best practices, which you'll learn about tomorrow. So some things that we could do to fix this would be modifying the program to take many input files, but a lot of programs and software that you might be using, you aren't actually able to make changes like that. It's either you didn't write it or it's proprietary, and there's all sorts of reasons why you might not be able to make changes to the source code. Another option would be to write some code or a script to automate some of that repetition. This could, in theory, be done in any language, but Bash is universally available on Linux systems, such as the National Computing Clusters, and it works well with the job scheduler, which we'll learn about a little bit today, but mostly tomorrow. And so Bash is the language for the job here. And so I will go back to the terminal. So let's have a look at our first script. So I'll use the cat command again to look at this run-numal script that we have. I'll say cat run dash, and I think I should be able to tab. No, apparently not. Run, there we go. Cat run-numal. We'll have a look at what is in this script. Here are the only two lines that are in that script. So the first line starts with this hashbang or shebang symbol, hashtag or number sign, followed by an exclamation point /bin/bash. This tells the system how to interpret the code that follows. So this could be bash, this could be Python, this could be a different type of shell, etc. In our case, it's bash. And so next is the actual code that the script is going to be running. So it's exactly the same line that we were typing, that we were entering earlier up here. /numal methane.in, methane.out. So yes, even though we've put this line in a script now, it's still not very useful for reducing repetition because now we'd still have to edit this run-numal script every single time we want to specify different input and output files. So this is because our file names we have here are hard-coded, meaning that the value is fixed and it can't be changed without modifying your source code or your program or script directly. And so this is something we usually want to avoid when we're programming because it greatly reduces the amount of flexibility that you have when you're using your scripts. And then as we can see so far, it doesn't actually do anything to alleviate our current efficiency problem. So what we can do is use a variable. So in programming in general, variables are used to store information and pass information to other programs and functions. So if you need to use a piece of information in more than one place, especially if that piece of information is going to change from time to time, it's best to represent that information with the variable. So in our case, we have a really great candidate for variable replacement with our input and output file names, this methane part. We want to be able to replace that with other molecule names. So there's lots of variables in the shell that are already defined, and we can also define some of our own. So let's try printing a shell variable with the echo command, which is essentially the shell version of print if you've done other programming. So I will show you, we will type echo space and now $, that's the symbol bash uses for denoting variables. And then in all caps, we'll do bash underscore version and hit enter. And we're all on the same computer, so I would imagine we'd all get the same version. So we printed what the bash version is, 5.1.8, parentheses 1. So we can also try defining some of our own variables in the shell. So to do this, we set them using the equal sign with no spaces around them. So I'll try pet equals Fido, enter. And I don't get any output. I wasn't expecting any. So we're good so far. Next, we'll try legs equals 4, enter. This time again, doesn't say anything, but now we'll try using them in an echo command. So we'll try echo $pet, because we need the value of the variable, as $legs. So it should substitute those values for pet and legs where we have it noted with the $, to tell bash that it's a variable. So you're here, and excuse me, we do get what we expected. Fido has 4 legs. Just for demonstration's sake, I'll bring this command back and I'll get rid of the $. Run it again, and we can see this time it's not realizing that pet is a variable. We have to use those $signs to tell bash. Yeah, we want the value that's been stored here, not just the name. Okay. Questions so far? What questions do we have? I think they're all getting answered in the chat. I can look at the chat a little bit, but not a lot. So you don't have to wait for me to ask for questions to ask. Pretty's good. I will carry on. So now we can edit our run-newmol script. So what we'll do, we'll open it with a text editor. We'll use nano, and we'll replace the molecule names with special shell variables. So I'll type nano. That's the particular text editor we're using. And all right, run-newmol. And I'll leave this for a second because once I hit enter, my terminal's gonna, you won't be able to see my command history. So we've opened it up in nano. So you can see it's the same 2 lines. This is what we expected. But now I'll focus back to the slides again. Go. Okay, so this slide shows us how we're going to edit our script. So we're going to use these positional parameters, these $ones here. And these represent the first argument that we'll input when we're executing our run-newmol script. So $2 would represent the second argument, and so on and so forth. So this way we don't have to actually, we can see the example of how they ran it here. They ran it with bash, run-newmol, and then they gave methane as an argument. So since this is the first argument, methane would be replaced where this $1, where both of these $ones are. And you can add more positional parameters within reason. So we'll edit our script to match this. So I'll bring my terminal back. I will use the arrow keys to navigate through here because this is a totally keyboard-based text editor. It's very, very basic. I will backspace these methanes, replace it with $1. I'll leave the dot in and the dot out. I'm only getting rid of the methane part. So once we have this to save, we can see there's some stuff. We have like a little menu down here. Of course, we can't click anything. We have to use the keyboard shortcuts. So to save, it's this one here, Control O to write out. So I'll write Control O, the letter O, not 0. Once I press Control O, it prompts me to check the file name. So it's run-numall. As long as that's good, you can press Enter. There we go. And so now it says I wrote 2 lines because this file is only 2 lines long. And then once I have it saved, I can press Control X to exit. So you can go ahead and exit and get back to your terminal. I'll wait a second. If you could give me a green check mark once you've edited the script, you saved it, and you're back at your terminal or back at your command line. So it's Control O to write out, Enter to confirm the file name, and then Control X. And if you're stuck, also let us know. Control X now to exit. So I'm back. Now we can execute run-numall again, and we'll give the molecule name as an argument. So we can use a different way to run the bash script by typing bash, followed by the script name. Run-numall. Yeah, there's a good question. What is Nano? It's the name of a text editing program. It's very, very basic. There's a few different ones that are popular with Shell and Linux users. Nano is a super basic one that's really good for teaching specifically. Yeah, Manager mentioned Vim. That's the one I used in grad school that is also pretty popular. And you can do a lot more things. There's lots of different text editors. It's a matter of preference, pretty much, and what you need to do with the text. But yeah, Nano's the one we use in all of our training. So I'll type bash, run-numall, and now we have to give it the argument, methane. And we don't have to type methane.in because remember, we still have that in our run-numall script. We just need the name itself. The .in and .out is still inside of our script. So I can hit enter, run that. It'll take a few seconds, but now it's done. So our script is no longer hard-coded, so we've saved ourselves a little bit of time and effort, but we still need to type the molecule name every single time, which is still not ideal, but we're in a slightly better spot than at the start. So another way to improve our efficiency is to use loops. So loops are a programming construct that allows us to repeat a set of commands for each item in a list. So if you've done any other programming, you've probably encountered loops in some way, and they're also very popular in the shell. So they're pretty essential for productivity improvements through automation, which of course is one of the main reasons for learning the Unix shell. And loops reduce the amount of typing required to do things, and because of that, reduces your likelihood of making mistakes, and it improves how reproducible your work is. So I'll pop up to the slides again. to the loops section. Yes. So when we do a for loop when we do a loop in Bash, the word for indicates the beginning of the for loop command. So we have for something in a list of things, in this case, for molecule in our list of molecule names. And then on the next line, the word do indicates the start of the command execution list. So whatever commands you're trying to run on each line, each item in the list that you specified. So after you've written all the commands that you want, on the next line after that, you put the word done, and that signals the end of the loop. So I'll bring my terminal back because we will do our own loop. So we'll start typing on. So I'll start with for molecule in, and now I'll give it my list of molecules, which is just the 3 that I have. So in ethane space methane space propane, enter. So note that our prompt has changed from a $sign to a greater than symbol. And so the shell is sometimes a little bit smart and it can tell that we're writing a multi-line command. So next, you write do, enter again, and let's add a line that echoes the molecule name that it's working on so that we can track the progress of the loop. So, okay, I see some people are still stuck. I'll finish this and then I'll demo again, exiting Nano. So we'll do for, or we already typed for, sorry. After do, now we'll write echo, working on $sign molecule. This will just be helpful for us so we know what's going on. Next line, bash, run dash newmol, space, $sign molecule. Enter. Done. So now, once I hit enter, this for loop should execute because Bash will realize, okay, yes, we've actually finished writing out our full for loop. Enter, and it's echoing working on ethane. So now it's doing bash run dash newmol ethane. It'll take some time. Now it's working on methane. And then it'll work on propane. Our prompt comes back, then that's when it's done running. Yeah, for the people having issues getting out of Nano, you Control O to save, but then you have to hit Enter to confirm the file name because that's the prompt that'll come up at the bottom. And then once you have that wrote 2 lines or that wrote however many lines message, then you can do Control X. Anybody who's still stuck, please let us know. Here, and we can see now we have output files for all of the other molecules. So we've made things a little bit more efficient for us, but we're still typing out each molecule name manually, and we don't want to do that. Remember, we're pretending that we actually have 300 input files or some arbitrarily very high number instead of just 3 that we can see and count and type. So instead of typing the molecule names in our list, let's generate a list of molecule inputs and put that in a file so that we can use that as our input. Before I move on, what questions do we have about loops? Or, there's a question, what's the purpose of the echo working on $sign molecule line? It's to help us see what's going on in our loop. Because if we didn't have this line there, it would just be running with no output until the command prompt came back and we would see that it's done. It's mostly to help us kind of visualize what's going on with the loop and then know where it's at. Should I ask, what is bash for? Do you mean bash specifically right in this line or like bash in general? Ah, that's how we're telling it to run a bash script. So this is just another way of specifying like language and then script. You could run a Python file this way by writing like Python and then whatever the script name is, .py. This time we're doing bash run numall. It's another way to run bash scripts instead of the / way we did earlier. Did we edit run numall to read $1 instead of molecule? That's something actually I'll say hold on tight for that answer because we're gonna do more in editing that run numall script. We still have more improvements to make to our workflow. So the next thing we're going to do is we're going to automatically get our list of molecule names. So to get that full list of molecule inputs, we could use the wildcard. So what I'll type is I'll type ls asterisk .in. And so this is asterisk is a wildcard. So we're going to list all of the files in our current working directory that ends in .in. So in theory, this is all of our input files, whether we have 3 or 300 or 3000. So when I type ls asterisk .in, I get my 3 input files. So what we can do then is we could redirect this output to a new file that we'll call test set. So I'll use my up arrow key, get that command back, redirect this output to a file I will call test-set. Yes, Jacqueline, that's exactly it. So it's for thing and list of things. The first line we did in our list of commands was to tell us what molecule it's working on. Next was to run the script. And then you have to finish a for loop with done. I ran my command here to send that list of input files into its own file. I'll use the cat command to have a look at test set just to double check. And it's a list of our 3 input files. And in real life, this could be a list of 300 input files. So with the way that we have our run-numall script set up so far, we don't want all of these .in file extensions at the end of our molecule names. We just want the name on its own because the .in and .out are already written there in run numall. So we have to strip these file extensions off of all the file names in the test set file. So there's a few different ways to do this. I think by the end of this workshop, we'll show you 2, but the first way I'll show you is with Nano. So I'll use Nano to open this test set file. I'll just wait a second to open it up. Test set. Let's have a look in here. All right. So one thing that Nano can do is it can do file find and replace with control \. So I'll hit control \, on here. And now I have a prompt at the bottom that says search to replace. And so what I want to search and replace is .in. So that gets entered there. I'll do this really slow, only because it's hard to redo. So control \, and then .in, enter. Replace with, now it asks me what I want to replace it with. I don't want to replace it with anything. I just want to delete the .in from each line. So when it asks me what I want to replace it with, I will just hit enter again. So now it shows me the first instance highlighted in yellow. It asks me, you want to replace this instance? I can press Y for yes, N for no, or A for all because I want to get rid of all of them. So I'm going to do that. I'm going to press A. Because there's only 3 lines, I could just press Y 3 times, but we're pretending that we have many, many more files. So we'll do the efficient way. So now I've hit A. Now it says I've replaced 3 occurrences, and now I can do the same thing. I can Control O, save, and then Control X. So has everybody done the replacement and they've deleted .im from all of their files, or not all of their files, sorry, all of the lines? You give me a green check mark, and you can go ahead and exit Nano. I'll demo exiting Nano again. Anybody still working on doing the find and replace? Done this. I will Control O. Wants me to confirm the file name, test set. Control O asks you to open a file. Is it this message here? Or is it something else? If you could let us know exactly what the message is. But now this wants me to confirm the file name after I've pressed Control O. I just have to hit enter because it's the same file. And now that I have this wrote 3 lines message, that lets me know that it's been saved. Okay, awesome. It lets me know it's been saved. I can Control X and I'm back. So once everybody's back out of Nano, I'm going to clear the feedback. Once everybody's back out of Nano, if you could give me a green check, and we're all back at our command line. Nobody's stuck. It's very easy to get stuck in the text editors. Okay, so we successfully removed all of these file extensions. So now what we can do is we can write our for loop so that we're getting the list of molecule names from our test set file instead of typing out each item. So what we can do for this is we can do this with command substitution. I will just, yes, this was the slide for doing the find and replace command substitution. So what we're going to do is we're going to substitute the output from an enclosed command inside this $ parentheses here, and we'll substitute that result into the outer command. So I will bring back my terminal because we're about to type exactly what was on that slide. So I'll try cat test-set again just to see. Now the contents of test set is just the molecule names. It doesn't have that .in anymore. So what we can do is we'll type a new for loop. We'll try for molecule in $. I'll set up both my parentheses and then I'll use the arrow key 1 left to move inside and type in there. So the command we're going to be substituting into this for loop is cat test-set. So whatever the contents of this test set file is what's going to be our list for our for loop, our list of things for the for loop. Enter. And now I can type out the rest of my for loop. Next line is do, enter, echo, working on $ molecule, just to be helpful for us. Next is bash, run dash, do mol, $ molecule. Next line, done. So wait a second, run this. It takes a little while to run anyway. I'll hit enter. And now we should see pretty much the same output because we haven't changed what we're doing. We're changing how we're doing it. Now we don't need to type out all of these molecule names individually. We have a way to collect them all automatically. So if your for loop ran and you got the same output as me here, if you could give me a green check mark. Slide is a little bit of a review just to look at everything we've done so far. What is it? What exactly is Bash working on in the 3 files? You can actually have a look at the Numol script. This is kind of an ugly way to look at it, but this is what's in the Numol script, and this is our pretend script. This is actually a script, I think, or an actual program I think Ross worked on that does real chemistry. But yes, it's getting essentially what it's doing is it's getting the number of atoms in the molecule and then echoing the message, this is Numol, sleeping for however many seconds, that is the number of atoms in the molecule, and then just printing the energy, which is still just the number of seconds that it slept for. So that's what's actually happening when Numol is running, but we're imagining this is some program. It could be anything, really. Okay. I hope that answered your question. Happy to talk about it more too. So we'll do a little review of what we've covered so far. Some of the things that we've done, we learned about redirection of the input and output using the greater than, less than symbols. We set variables and use them in different commands with the echo command. We also learned positional arguments, which are super handy. We talked about looping, which is maybe, for me personally, that was the thing that I used the most all the time when I was doing things on the shell. That's very, very handy. We also talked about wildcard file matching, and we looked at command substitution. So what questions are there about any of these things so far? We'll also have time at the end for questions. I think we're making pretty good time right now. Almost done with our workflow. The next thing is how we're going to actually collect all of our results. So right now, all of our results from our Numol calculations are all in different files, but we want to collect all of the important information together. So we could check our 3 output files. First, I'll try ls *out. And we see we have the 3. Imagine we have 300. We can also try another command for checking the contents of a file is the head command, which is handy. That prints the first 10 lines of any given file. You can also change the number of lines, but we're fine with 10. These output files are short. So I'll try head *out just to have a look at what all of these files look like. So they all have the same format. This is Numol hitting, the energy is, and then we have a number. And so we want to grab this line with the energy and collect it. So to do so, we'll use the grep command, which searches files for the pattern given as the first argument. So I'll start the command. We'll type grep, and then in single quotes, The pattern we're going to be looking for is energy in those single quotes. And then now we have to give it the file name to search. So we want to search all of these output files. So asterisk dot out. When do we create the dot out files? Those were created when we ran numall. I'll run this just so that I can run it and get it back. And here we have our ethane dot out. So this is our output from grep. It says which file it came from and then the line that we were looking for. So if I look at the run numall script again, I'll just cat this so it's here. So we created the output files when we redirected the output to our positional parameter argument dot out. So when we were doing the for loop and it was running this script for each item in our list or each item in our test set, so our 3 molecules, every time this ran, it created the output file. It's just now we don't actually see this happening anymore because it's within our script. Okay, so we did get our grep result that we wanted. What we can do now is we can send this to a file we'll call raw energies. So I'll bring back this command, our grep energy star dot out, redirect that to raw dash energies. Enter. So now we'll have this result here saved to a file. So we can use another editing method. What we want to do now is we want to chop out this middle bit here. This dot out, the energy is, blah, blah, blah. We don't care about that. We just want the name of the molecule and the result. So to do this, we'll try using the sed command, short for stream editor. So this is another way. We could do this with nano again, but this is the better way, especially if you're going to be using it within a script. So I will type first, cat that raw energies file, just so we're looking at it again, and it's right there. I'll type sed, S-E-D, space, single quotes, and then inside those single quotes, I'll type S /, and now we want to write out the pattern that we want to replace. So that's from dot out all the way to the energy is. You could copy and paste that, or you could type it. I'm just going to type it for now. So dot out, just make sure that it's perfectly, it's case sensitive, so make sure you have it exactly as written. Dot out, colon, the energy is. And now another /. And so this would be where we want to write what we're replacing this line with. So everybody hold tight for a second. I'll demo this. I'll replace it with the word test, but we don't actually want to replace it with anything. We just want to see. So we're doing this with raw energies file. I'll hit enter and we can see we've found this dot out, the energy is, replaced it with test. We don't actually want to replace it with test. I'll bring back this. I will backspace that. So this is what our command should look like. So we have single quote S /, and then this is the pattern we want to replace. Dot out, colon, the energy is, / again. Now this is, after that / is where we would replace something. We don't want to replace it with anything. So you do another /, single brackets, and then the file. Now if I hit enter, now the set output is what I wanted it to be. Ethane -8, methane, -5, propane, -11. Already missing the raw energies file. You probably need to run this grep line again and make sure you redirect the output to the raw energies file. This guy here. I can copy that into the chat too. I get a green check mark if you got this output from Zed. Zed is a really handy command that can do a lot more than just substitution. I think I only used it for substitution. This command into the chat too. The formatting can be key. We ran that, but look, if I check the contents of that raw-energies file, it's not actually changed because Zed doesn't edit the file. There's a setting, there's a option you can add to make it edit the file, but it's not good to do just in case. If you mess anything up, then you mess up your file and you don't want to overwrite data by accident. So I can see it's still actually the same. This Zed result just printed to the terminal. So what is Zed for? It's a command for, it stands for stream editor. It's used for a bunch of different ways of finding and replacing, editing text, or editing files. Maybe if someone can find the like a man page or something for a Zed. Yeah, it's a command used for editing files basically. But it's very, very flexible and has a lot of different ways you can use it. This is just one of many. Side. We already talked about using the up arrow to go back through your command history one by one. You can also use the history command with some number as an argument to display the last number of commands you entered. So I could do history 5, enter, and I can see the last few. History 5 is still the last command that I entered. So really the last 4 commands that I actually did. But that's one useful way. Is the methane dot out? Yeah, I think we'll have to have a look at the run newmol. Something, yeah, okay, James, you got it. Something's afoot in the script, it seems. Okay, the next big thing that we're going to talk about is how to join commands together. Are there questions, more questions about sed or grep? They're both super useful. Another one that I think is in sort of the same category of command that we're not going to talk about today is the awk command, AWK. That's also useful for editing. If you're interested, you can look up how to use that one, but it doesn't get covered. Is it possible to permanently clear the history? 100%. I assume yes. It shows the history for your current, I guess, shell session. So if I logged out of the training cluster and logged back in, it wouldn't show me the history of what I did right now. It would only show my current history. I'll let a helper give you a better answer for that one though. Okay. So the next part is joining commands together. So we did all this. we got our nice answer. Oh, I forgot to do something. Okay, let's use the command history, bring back, yes, bring back this sed command. We want to save this to an output file before I move on. So bring back this sed command where we're getting rid of the energy is, replacing it with nothing. We want to redirect this to a file called results. So now if I cat results, we have that there. Excuse me. We just want to save that before we move on. So now we want to eliminate the need for that intermediate raw energies file. So we can do this by joining commands using pipes, where the output of one command becomes the input for another. So we want our output from grep to become our input from sed. Here we go. This demos what we're about to do. We want our output from grep to become the input of our sed command. And so we can do this with this line of code that we're about to enter. So I could go back in my history to get half of this at least, but I'll type it out. We'll bring back grep, single quotes, energy of all of our output files. So asterisk dot out. Next is we need the pipe symbol. So for me, it's on the same key as the backslash. So shift backslash, at least on an English keyboard. If you have a French one, I'm not sure. I'm sorry. So the pipe symbol is a vertical line. And now we'll type out our sed command, sed, single quote, s slash, that same pattern we want to get rid of, dot out, colon, the energy is, slash, again, another one, because we're not replacing it with anything, single quote. And we'll redirect, well, I won't redirect this yet. I'll leave this for now. So notice this time we don't need to specify the file that sed is working on because it's working on the output that grep is giving it. So it's receiving input from the previous command in the pipeline instead of receiving input from a file name argument. So if I hit enter here, I should get this same result. Ethane -8, methane -5, propane -11. Perfect. So now I'll bring this back. I think I actually saved the results too early. It's okay though. I can save it again. This will overwrite the results file, but this is the only thing. It's the exact same. So now I'll bring back my pipeline, save that result to a file called results. So once you have this pipeline entered and then save that to the results file, if you could give me a green check mark. Pipelines are another useful tool. Yeah, and James added a really good point. You can get more about a command by doing dash dash help about a command. I think sometimes I think this gets talked about in the yesterday's session. Sometimes on Mac versus Windows versus Linux, it might be different. Like man, short for manual, sed, or sed dash dash help. Those are two ways to look for help. Yes, I'll copy this line into the chat. It's long. Already typed out all the parts individually. Okay. So we'll have a look at another little review. So we did more things. We used grep to search files for strings, sed to edit a text stream. We did specifically replacement or substitution with sed, and we also did that with nano, not vim. We used the history command to look at prior commands, and we did a command pipeline where the output of the first command becomes the input for the second. There's a good question. What is the use for pipe? It eliminates the need of having intermediate files, depending on the pipeline is pretty flexible. But yes, before we had to save the output of command one into a file and then use that file as the input for command two. But we don't have to do that. We can smash them together right away, and then we don't need that intermediate file. In our case here, since we only have a couple files that we're doing this with, it wouldn't be a big deal. But then when you're working at scale with lots and lots and lots of files, and then suddenly you're creating thousands of intermediate files, it slows down your work essentially. So it's a time-saving thing that might not be so obviously necessary in a small scale example, but then all those intermediate files would add up really quickly once you start working on real data. What questions do we have about any of these topics or anything from before? We're almost done. All of our scripting. So we have the story up to now. So we've very kindly provided a script that has everything that we've done so far all put together. So if you have a look at the run-all file, you can see it's a bash script. This is the script printed out, so I'll look at it here first. So it's the bash script indicated by this first line, the hash bang /bin/bash. Run all, it'll put the numol energy for all.in files into results. So it starts with ls*.in, pipes that into the sed command to remove all those .in file names, sends that to a test set file. So when we did this earlier, we didn't use sed. This is when we use nano to get rid of it, but sed works just as well, and it works better in a script like this because we don't actually have to open a text editor, edit it, and close it. Then we have the for loop to run numol on all of the molecules in the test set, which we did before. It still has that working on molecule, and then numol molecule.in, molecule.out. And then we use our pipeline of grep into sed to get the list of molecules and their energies. So this is that same line that we just ran. So I'll bring up my terminal again. ls, and you can see, where is it? Run all here. I'll use nano to open that. No, I won't. I'll use cat to look at that run dash. Here, it's that same script. So the hash bang collecting the list of input files, stripping that .in off of it, saving that list to our test set, our for loop with command substitution, and then using the grep and sed pipeline to get the energy, to collect up all the energies. So how are we doing? Right now, we have the tools to automate repetitive actions using scripts, variables, and for loops. We can also extract and combine results from multiple files using grep. We can edit streams of text to remove unwanted stuff. We did that with sed. We also did that with nano. And we can combine commands using command substitution and also with pipes. So the last thing that we haven't talked about yet is how to interface with the scheduler. So I'll give you, I guess, a little sneak peek of tomorrow's session when that's all about using the job scheduler and how to all the different fun job scheduling things that there are to learn. But we'll do a little bit today just as a bonus. Okay. So we'll start with, well, yes, now we can start thinking about how we would incorporate our workflow that we've now established and we've done a pretty good job with into a job script. So a job script is a special shell script that includes instructions for the scheduler. So we can write, what we'll do is we'll write a simple one called newmall job, and we'll set it up like this. So I'll bring back my terminal and we'll write this job script. So I'll use nano newmall-job, which is not a file that exists so far, so it should be a blank file that it opens. Nano newmall-job, enter. So now I start typing out my script. So I start with the hash bang slash bin slash bash. Enter. How can we comment out a line of code in bash? Ah, it's with the hashtag comment. Okay, yes, lots of people answered in the chat as well. Awesome. I say that, and now the next line we do, the specific thing for giving directions to the scheduler starts with a hashtag, and we do capital SBATCH, SBatch. And so don't worry too much about this SBatch line because that's what tomorrow is all about, and you'll learn lots about it. So SBatch space dash dash, giving right time equals 0:30:0. That means we're asking for 30 minutes. And we'll write dot slash, we'll go back to our original way of calling newmall less than do $1 dot in greater than $1 dot out. And this is our completed job script in this instance. So maybe what I'll do, I'll copy all this into the chat also. I have this ready. I'll save and exit. So Control O. File name to write is newmall-job. That's correct. I hit enter. I've written 4 lines. And then when I'm ready, I can do Control X to exit. So once you've exited once you've exited Nano and you're back at the command line, if you can give me a green check, I'll leave mine here for a second for anybody who's still typing. So once you have this typed out, Control O to save, enter to confirm the file name, and then Control X. Awesome. Okay, so now I'll exit Nano. So now the command to submit this job is SBatch. So SBATCH. Then we do our job script name, which is newmall-job. And we still need to give it that positional parameter. So we'll use methane again, just because. So before I enter this, only because I know these jobs don't take very long and I want to see it in the queue after I run it. The command to check the queue is SQ. SQ. So SQ like that, spelled out. That'll show you the that'll show you the queue for the entire cluster. Or you could use SQ, just the letters, to see your personal queue. So only the jobs that you've submitted to the queue. So I'll go ahead, we can all hit S batch. So now I've submitted batch job 9. So this is only the 9th job that's been submitted on this whole cluster. I'll try hitting SQ. There we go. So we have a few, user 5, user 9, 33, and 7. We can see these ones are running. They have 29 minutes, 56 seconds left. These ones are pending. You'll learn all about this tomorrow, but it's awesome. We got a few things, and now the queue is empty, so everything's done running because these jobs are very, very short, not like in real life. So we submitted a job to do one run of NuMall, but we can loop inside the job script as well. So let's go back into NuMall-job, our job script, and we'll edit it. So I'll use Nano again. Nano, what is that? NuMall-job. So what we'll do here, around this, we'll switch it. We'll add for molecule in $, cat test set, because that file still exists. Do. So now we have our run NuMall line. Ooh, we have to change these positional parameters though, because it's not positional parameters anymore. So we still have our $sign for the variable, but what we're going to do here is we're going to write molecule in curly braces, curly brackets. So this is so Bash doesn't get confused and think that you're trying to tell it that this molecule variable, just so that it doesn't get confused with the dot in and dot out. So I've made that edit. On the next line, I can do done. I'll copy this into the chat again too. So we're writing this so that it's a for loop. And we had the $1 needs to be $sign molecule with molecule in curly braces. So you can save and exit. Once you've saved and exited, after you've edited it, if you could give me a green check mark again. Start saving. Control O, save. Why do you have to spell out from 1 to molecule? Yeah, because now that we're doing this in a for loop, we're not going to be giving it any arguments for the molecule name anymore. Now it's getting that molecule name from the for loop, from checking the test set. So now next time we submit this as a job, we don't have to submit it as a job with that methane argument or ethane or anything else. Okay. So I'll control X now. So now we can type sbatch NuMall-job, and we don't need to give it any other arguments. Like up here, we gave it the argument for methane, but now we don't need it anymore. I'll use SQ to see the full queue. And we have stuff running and pending. Awesome. SQ to see just your own. So here's me. SQ spelled out. to see the queue for the entire cluster, which on this training cluster is only us in the workshop. If you log into one of the national systems and do this, it goes on forever, it feels like. Okay, so the last little thing that I'll talk about, just because we still have a few minutes, another fun thing, you could run all of your short tests with a job array. So this method is particularly well suited if you have lots of small jobs that only differ by one parameter. So in this case, all of our jobs are the same. We just need a different molecule name. So there's a sample already there that you can try running. Yes, this shows some job array stuff. There is a job array already by ls. There's this guy here, array-job. I'll open it in Nano just to have a look and show you what's in there. So to submit this job, it's sbatch, the job name, so array-job once, and it'll run all of the molecules in the test set. So here it's 5 minutes per job, and there's 3 jobs in the array. So it's grabbing the molecule name and it runs new mol on the molecule. This line here should look familiar. And you can see here there's command substitution too with variables. So I just wanted to show you that. You can try it out. You can try sbatch array-job. And now if we do sq, oh yeah, we have a bunch of people that submitted it. Awesome. These run pretty quickly again. Oh, to the end of this workshop. So the last thing is to talk about where to go for help. So the technical wiki, docs.alliancecan.ca, is maintained by the staff, both at AceNet, the Alliance, our other regional partners, and that always has the most up-to-date information on how to run specific things. There's all sorts of different examples, and there's lots of support for different programs that are popular in different disciplines as well. So the technical wiki is always a really good place to start when you're looking for information specific to working on the national systems. There's also the helpline, so you can email support@tech.alliancecan.ca or support@acenet.ca if you have specific questions. That connects you with our team of research consultants. Sergey here, that's a helper. He's one of those research consultants that we have all over Atlantic Canada at different universities. And as well, there's the team across the country. And we also ask that you help us help you. So if you submit a ticket and you're getting help, or you email, say, our training email, training@ace-net.ca, please let us know how helpful we were so that we can do a better job for you. So that is the last thing that I wanted to talk about today. Tanya, I think the floor is all yours. You can stop the recording.